Okay, so welcome to those of you watching from home. So we're at the Williams College Museum of Art. We're here with a friend of my family, Liz Gallerani. Our kids have known each other for six years now. And so she's going to give us a tour of some of the pieces here, and we're going to use this as a springboard to talk about some of the things we've seen in complex, and you've seen in some of your other classes, possibly statistics classes if you've taken those, and what we're going to be seeing next week in complex.
So without further ado, let's head upstairs.
And you can just get some like general shots as we're walking.
Oh yeah. Of the solo in progress.
Yes.
I guess it's done now, looks like.
With certain object files. I'll take everything that's on. Thank you. This is our brand new wig.
Almost done.
Just finished last Wednesday.
You know, there's restrictions as to who's allowed to have these displayed at the same time.
I don't believe so. That's
Okay.
a really good question. I'm almost positive that there are definitely ones that are up because Mocha has almost 100. Some of those are up in other places.
See, take a look of it. It's not a C, it's an L. I'm positive it's an L.
Yeah, so my understanding was that was part of what was interesting about Solowit's work was that he doesn't actually create it, he just kind of makes the instructions.
So conceptual art is all about the idea and not about the maker. And
Right.
at times where it's so much about the artist's hand, to the extent that, Durer himself didn't necessarily engrave or carve all of those plates. It's his art, but there may have been other people involved. Wit, and we're going to be right here, Wit is all about, I came up with the schema, now you all bring people from your community together and make it.
Right, I'm a big ideas kind of person.
Yeah.
Yeah.
So just looking with the second highest course number listed.
So this is Object Lab. This is a pilot gallery that I created for this fall. Your professor was one of the 10 who was willing to be part of this pilot, but an opportunity to have art out for students for the entire semester. So instead of, the luck of does something that works with the class happen to already be on view, here proactively we can make sure that it is on view. So we have 10 courses right now. It is way too tight and full, so we're going to go back down to about 7 courses for the spring, but especially great for Div 3 and with labs, just another way to involve more students in looking at art.
So why don't we move over here so we can see the main picture. So I'm pretty sure this is not titled Complex Analysis by myself. If so, can I take it home with me? All right, so do you want to, I'll let you come in
Sure,
and then
yeah,
zoom
we'll
and then just walk away from it.
We'll get a shot.
Just try to get, what happens when you get very close to it? So get really close.
All right, really close.
Really close. As close as you can. You can get close. There you go.
All right, little speckles.
Right. Excellent. So why do you think we have this here in a complex analysis class?
Feel free to get really close to it too.
Take a moment to look
Get
at it.
nice and close in there. It's your print.
It's your print.
At least for right now.
So does anybody know what kind of style this is? Okay. So what does that mean? I'm a cultural philistine.
Yeah.
You
Art
love-
historians love isms, so what is that particular one?
You paint with a bunch of points.
Okay, you paint with a bunch of points.
So what happens when you look up close at the points? Like when you guys get really close to it,
They just
as I
look
know
like
you want to.
points.
They look like points.
Right, you just see dots, right? So in this particular one, what colors do you see when you're looking really up close?
So you see mainly blue and yellow.
Yellow and orange.
Like this yellow, orange, kind of saffron color, and then this kind of bluish color in particular, right? And then as you stand further back, what happens to the points?
Yeah, it seems like the start is almost just primary colors, and then fade into other shades as we step backwards.
So do you know how many distinct colors are in this picture?
This particular one, no. Most of the dots are primarily those, though there are some different shades. The yellow-orange appears to be the same shade pretty much throughout.
Okay.
The blue changes a little bit. But yeah, as you go further back, kind of crystallizing into this view of London, But then also, as you mentioned, seeing different colors as well, that it's not just those more basic points that you're seeing, kind of blends together.
Now, where have we recently seen something where we've been using color to indicate something?
Well, I guess if we're going to try to represent complex functions, then we can use colors to represent the modulus of the value, and then different hues to represent the
Right. So this is one of the big problems we have. So right now we've been doing complex analysis. Complex analysis is in some sense very similar to Calc 3. Why is it similar to Calc 3? You do a lot of integrals. And what big theme do you have in both Calc 3 and complex analysis?
It's Green's theorem.
You have Green's theorem. So you have Green's theorem that you have these integrals along closed curves. And if the function has zero curl, these integrals are trivial to evaluate in Calc 3. These line integrals are just zero. A holomorphic function satisfies the Cauchy-Riemann equations. These integrals will be zero. And this allows us to do these calculations. So you can regard complex analysis not as a course about one complex variable, but about two real variables with a very special link. Now, Calc 3 is all about taking functions of one real variable and generalizing and seeing what happens as you go further. In one dimensions, a limit is not that exciting. Right? You go down, you go up. That's it. In complex analysis, why are limits more exciting?
Well, it's not going to matter what path you take.
Well, it's not supposed to. You're supposed to have the same answer no matter what path you take. And so when I teach Calc 3, I actually have, for years I would have my kids when they were in the children's center, their classes would be like slave labor. They would make scribbles of just lines all over the way getting towards a point. And your limit has to be the same no matter what path you take. And so having a limit that exists in complex analysis is a much stronger condition than having a limit that exists just in one line. Well, we went from one line in in Calc 1, 2 to multiple dimensions. So what do you think comes next in complex? What should we do next?
Add another dimension.
Imagine the dimensions, right? So in Calc 3, we have functions of x1, x2, x3 through xn. So in complex analysis, we should have functions of z1, z2, z3, all the way to zn. Now we saw things had a phenomenal change in real analysis when we went from one dimension to two dimension. Limits were no longer trivial. A limit existing implied an enormous wealth of information. And in fact, in one dimension, if you have a singularity at a point, you have no way to get from one side of it to the other without passing through. But if you're in two dimensions, you can say, oh, screw that, and just bypass it. All of a sudden, when we go into complex analysis in several variables, it is a completely different story as to what happens. So if you thought complex analysis in one dimensions was strange, wait till you see on Monday what comes next. So the question is, how do we visualize this? We can't even visualize things well in just one complex variable. Now we have to imagine an n-dimensional complex space and try to get intuition. So that's why when Liz asked me if I was interested in collaborating and trying to come down here, I thought that this might be a good idea. I don't think we're going to be drawing pictures like this, but the issues that the artists have here in terms of how do they represent something using certain tools and techniques, I thought it might be a really good way for us to think about what issues do we have in representing things. How many of you have taken a stats class? Okay. For those of you who don't have your hands up, you should strongly consider taking a stats class before you graduate. I'm not supposed to say words like jobs, that's a four-letter word on this campus, but it is a great skill to have. One of the big things in the stats class is how do you visualize data? And you can do bar graphs, you can do pie charts, you can do histograms. Different ways of representing the data leads to different views. We often like to do log transforms when we do things in mathematics. that if we have a nonlinear relationship, if we take a log transform, it can often become linear. Kepler's third law of planetary motion is a great example. It's something like the square of the semi-major axis is proportional to the period cubed, or the other way around. But if you take logarithms and now look at the log of the semi-major axis versus the log of the period, it's now a linear relationship. So in complex analysis, as was said, we have two inputs coming in, say x and y, and two outputs coming out, u and v. So this is a four-dimensional blob that we need to picture, which we can't do well. So we have some tricks. So what are tricks we can do to visualize a complex function? So I think some of them have been said. What's one trick we can do?
Chuck some colors in there.
We can jot some colors in there. And so then we can somehow use the color to represent maybe where you're moving on the imaginary axis. Maybe draw like a unit circle and maybe have it red at one spot and have the colors slowly moving along the wheel, returning back to it as you go around. Or maybe not, maybe somehow take this into account as how much you're winding around. So we could try to use color to give a sense of what the function looks like, so that you can then look down and have a three-dimensional representation of this four-dimensional object. What else could we do?
Look at the real and imaginary.
We could look at the real and imaginary parts separately, and then that will give you a really good sense of what's going on, because if we look at just the real part, that's going to be a three-dimensional object. We can definitely picture those two, but then we have to somehow combine those two images in our head. There's something else we can do. We'll lose some information in doing this, but there is another way to try to plot a complex function. You'll lose information. The picture will not be everything. You could plot the magnitude. We could plot the absolute value of the function. And so in some sense, we can, this goes back to the color, is we now start adding the color to indicate the angle. And so it's all these different ways of trying to get a sense of what's going on, how can we visualize things. If you can visualize things, I think you are more likely to understand what's going on. We talked a little bit about fractal geometry on Monday. I was actually going to save that till we started doing several complex variables, but since the kids were in class on Monday, I wanted to show pretty movies, and I know Kim likes Wrath of Khan, it's a great movie. Why do we use colors for fractals? So it's a very fast comment. What was the color indicating in the fractal?
The rate of convergence.
Rate of convergence. So we had a very simple rule. If the point stays bounded when you keep iterating the function, we color it black. And if it goes off to infinity, we color it. And we color it based on how rapidly it goes off to infinity. What's the danger of something like this?
There's no real scale you can use to be consistent, I guess.
So one question is, what would be a natural scale for this? How do you want to choose your colors? Maybe it looks like something is going off to infinity, but it's just climbing for a long time and then falls down. Have you ever heard of the 3x plus 1 problem? So my favorite quote on this is, there's one by Erdős, mathematics is not yet ready for problems like this. And the other is Kakutani, who called it a Soviet conspiracy to slow down American mathematics. Because everywhere he traveled, he would speak about this, and people would say, oh, this isn't that bad. And they'd roll up their sleeves, and about a month later, they'd give up in frustration. So it's a really nice sequence defined as follows. Give me a positive integer. If it's odd, I multiply by 3 and add 1. And if it's even, I divide by 2. And then you just keep iterating. So somebody want to give me a reasonable number?
Let's say 5.
5. So 5 is odd. It iterates to 16, 8, 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1. How long do we have to fill? All right, another number.
7.
7. 7 is odd. You guys seem to like odd numbers today with 2 data points. Although there's a 50-50 chance you would have numbers of the same kind. 7 is odd, goes to 22, goes to 11, goes to 34, goes to 17, goes to 52, to 26, to 13, to 40, yes, to 20, to 10, to 5, to 16, 8, 4, 2, 1, 4, 2, 1, 4, 2, 1. This is 2 data points. This should be more than enough for you to conjecture. What do you conjecture?
That the sequence of points always ends up repeating 4 to 1.
It will always eventually end up 4, 2, 1, 4, 2, 1, 4, 2, 1. And we have 2 data points to support this. The conjecture is true. We don't have a proof of it, but it's true. Now you can also look at, well, what if you look at slightly different sequences? Would you still have this? And I can give a heuristic proof, and if people are interested, I'll give a heuristic proof as to why it's true. What's a good question you could ask now about this sequence?
How long does it take?
How long does it take? And so I am not competent to do mathematics in public if it's like addition and stuff like that. You know, if it's doing integrals, sure, I can do that in my head, but addition, no. Take number 27. It takes a lot longer for 27 to iterate down to 1 than you would expect. And if you go on this for a while, you can be misled as to what is the true behavior of 27. Does it escape, or does it come down? So when you're trying to color this stuff in fractals, when you're trying to determine, has this point escaped? Well, you can only do a finite amount of computation on your computer. You have to have a cutoff. And you say, well, I'm going to run it 1,000 times, and if it's at least this large after 1,000 times, I'm going to say this escapes. You could be making a mistake. What can you do to minimize your chance of making a mistake? It's a really obvious thing.
You can run it more times.
You can run it more times. And the more times you run it, the more confident you are that you haven't made a mistake. But just because you run it longer and it looks like it's growing does not mean that at some point later, strange behavior could set in. So when we're trying to determine what the colors are, it's not clear. Now sometimes we can actually prove that things will diverge. And sometimes we can prove that, well, if you're at least this large, we can prove that when you iterate, you're always going to go by at least this much of a factor. And then we can prove you'll go off to infinity. But there are other places where the behavior is very subtle. Another one we had was when we did Newton's fractals as to which root does it converge to. And after a while, it looks like it's converging to this root, but then maybe it's not stable, maybe it jumps to another one. And so we have to be very careful as to how we do stuff like that. So again, for me, the reason I wanted us to look at this is to just really spend some time thinking about how do we want to present things. And this is something we don't do that much in a math class. For the most part in a math class, we have our book, we go through things sequentially, we really don't have that much time to just stop and think about what we're doing. How would you view a function of 2 complex variables that outputs a function of, let's be nice and just say outputs a complex number. So you won't even have a complex vector value function. You now have 4 dimensions for inputs. What's our notion of connectedness going to look like? How can we try to get a feel, a handle on something like this? We can do a lot of the calculations formally. And to some extent, at some point, we need to do that because we have trouble visualizing. There's a great joke, a mathematician and engineer are listening to a physics talk by a string theorist who's describing the latest flavor of string theory, and at the time it was a 26-dimensional flavor. And for a while, numbers that were of the form, I think it was 8n plus 2 were very popular for string theory. So 10 and 26 were leading contenders. And the mathematician is just smiling and enjoying the talk, and the engineer is just pulling out his hair. And afterwards he asks, so how were you able to make any sense of this talk? And she goes, oh, it was easy. I just imagined n-dimensional space, and then I sent n down to 26. Most of us cannot imagine an n-dimensional space and really have a feel of what's going on. We can formally manipulate numbers, but we don't have the same geometric intuition. So what I want you to do is go back and think about some of the other math classes you've taken, and just how much have the visual clues really helped you in what you're doing. When we did Newton's method, I drew the parabola and I drew the tangent line, and you saw the tangent line hitting. And then I iterated again, and you could see how quickly it was converging. To me, seeing something visually like that gives a great flavor for what's going on. What do we do when we start looking at these higher dimensional spaces when we no longer have the same way of getting our intuition. What can we do to regain that intuition? You know, I wish I had the answer for this. I do analytic number theory, so I avoid a lot of stuff like this. But there are different games you can do, there are different mappings you can do. It's trying to distill what the key features are here. So if you look over here, how do you think they're trying to distill the key features with dots? Because they're not covering everything. What do you think we're gaining? What do you think we're losing in this picture? So what do we not have when you look at this picture?
Sharp edges.
Sharp edges, fine detail. I mean, look at some of the, well, I won't publicly say this, but at least the details are sharp here. There's got to be, yeah, let's look at this one up over here. Yeah, that, you know, to me at least looks like art. You know, you can see folds in the garments. You can see very fine shadings in the light. How much shading do we really get here in terms of the light? So when I look at this, we've lost a lot of detail. But what have we gained? Hopefully we've gained something. Does it look different if we go further back? Let's try walking all the way down. Does it look very different if you go all the way back here than if you're looking at it close up? I would say it does not look like the same painting all the way back here. You know, ideally I had asked, they were not willing to remove this wall. Something about load bearing. But over here, all this way back, it's a very different painting. Do you see sharp details now? You see more details. I mean, the boat in the middle looks a lot sharper now. Even the building, you know, the castle looks sharper. So my question, and again, I'm not an artist, so I will defer to other people. How do you paint with dots so that when you step this far back, the picture will converge? I'm assuming back then that you cannot remove the dots very easily if you put something in the wrong spot.
Well, and thinking about that, we've also got I mean, this is actually a great area too, just in terms of other art. So artists interested in optics and the way that the brain perceives color and shapes. And so playing with expectations of the viewer. What I like about the Vion that is that your professor selected, he's probably best known for being the half-brother of Marcel Duchamp, but he did a lot of great things in his own right. But you know, he's kind of encouraging you to move around and see that London view from all these different perspectives. So it becomes a very different work of art depending on where you are standing. And that's something that the crisp work of art doesn't do. So in terms of what you're gaining, that it has this amazing transformative power and almost kind of playing with the viewer in a certain way. Not necessarily forcing you to move, but also thinking about how hard it would be to do that. I can only imagine him doing dots and then like running across the room, seeing what it looks like, and then going back in again. So how do you get it just right so that these two dots make this other color, or make this boat, you know, seen from feet back as opposed to just inches away? I do not envy him this task. I mean, I think it can seem deceptively simple.
Right. Now, does anybody have any thoughts as to how you would do this? I have a couple of thoughts that, you know, as a mathematician, you should always be willing to conjecture. So I have deliberately not researched how this is done. I'm embracing my Philistine-ness. But does anybody have any conjectures as to how you would do this if you were the artist? I have a couple of thoughts that I can share. Anybody brave?
And there's probably things that you could do now that you wouldn't have been able to do in Jacques Villon's time.
I mean, now you could definitely use computers.
If anyone's seen the artist Chuck Close, where he's
Yeah.
pixelating things,
Sort of like this guy over here.
that's a Vassarelli.
Similar flavor to Chuck Close.
But so when I program, I have two windows open. The window for my main program and a window to try things. So if I was an artist, I would have a separate canvas and I would try a couple of things and step back and see, is this working, is this not working? Maybe try a couple of things simultaneously. And maybe after a while you develop some techniques, almost like little functions or procedures. Here's a procedure to do this, here's a procedure to do this, and just almost have these things as packages that I could use, right?
Well, and also, so an example here, these three are all a study for another painting. We have 4 other studies by this artist. Are they exactly identical? No, not at all. So different sizes, different materials used. There's a person here, there's not a person here, there's a cat here, there's a person here, but not a cat here. He's trying different things, and they're almost done, perhaps even simultaneously, but certainly within the same year or two. So being able to play with it, that I think so often we can see a final product, especially a painting, and assume that the person just had this amazing muse and this wonderful prowess and came up with it. That certainly can be
Right,
true,
right.
and not diminishing artists. I am definitely not one. But there can be process, there can be trial and error, and it's behind the scenes a lot of the time. Sometimes literally, if you look at a painting under X-ray, you can see changes that the artist made, even on the canvas, which can be very expensive for them to do.
Right.
So they might want to try it out on other pieces of paper or things like that first.
Now, what's a disadvantage of if you have a canvas and you're trying something out and then you're walking back, checking? What's a disadvantage of this? It's time consuming. What could you do to minimize the amount of time? So one possibility is use a mirror. If you had a mirror far back over there, you could be at the canvas, you could just look at the mirror. So have people use mirrors for something like this. So I will admit, email me that should go in the class comments. I was not thinking mirrors. To me, a mirror is an expensive object. I was thinking of something cheaper. What's cheaper than a mirror? Yes, well, no, not a person. Not a person. A what?
Assistant?
Not an assistant. There's a special name for something that used to be a person and will be a person again someday. But for a couple of years, they're not a person. They are not an intern, a graduate student. If you look at Rutherford's experiments on the structure of the nucleus, the alpha particles, the gold foil, if he chose graduate students for eyesight who could look for the scintillation marks and just see when the event happened. So one possibility is you could have just a paid aide who's far away and is telling you how things look.
Right, put the brush a little to the right, a little to the left,
Exactly.
make it a little bigger.
What's the disadvantage of having a person versus a mirror? Yeah, that person is going to start projecting their own stuff, whereas if you have a mirror, you can see yourself what's going on.
Trust.
Right. But it's how would you solve issues like this? I was talking with a statistician recently who does some work in hockey sports analysis. And one of the things he looks at is shots on goal, where are the places that are most effective? And so he has all the data from the NHL, from shooting in different places, what's the probability the shot goes in? What other data would you love to know?
The frequency of a shot in each place.
So you would want to know the count. So we know the count at each spot, and we know what fraction the shots go in. One of the highest percentage shots to do is, if this is the goal right here, is basically from right over here. Does this seem surprising that this would be a very effective place to shoot? Why does it seem surprising that that would be an effective place to shoot?
You're not going to get a clear view of where you're shooting.
I'm sorry?
You're not going to have a very clear view of where you're shooting. You're behind the goal.
Well, you're coming just from like right behind the goal and just flipping it over, or just very close to the goal. Why would you expect that to be a low probability shot?
You're really close to the goalie.
Yeah, you're you're really close to the goalie.
Theoretically, a
And if you're
goalie
shooting really close to the goalie, what is the chance of getting the ball right by the goalie? Very small. What do you think must be the case if that's a high probability shot of success?
The goalie's somewhere else.
The goalie's somewhere else. So when you see what percent of the shots are going in, just because a lot of shots are going in does not mean that's a good shot to be taken in general. It means under the typical situation, when people shoot from there, they're only shooting from there because the goalie's someplace else. So when you look at the successes, you would love to know at the same time, where are the defenders? And if the defenders are not there, okay, sure, take that shot. But the only people who are taking the shot, it's self-selective. They're taking the shot because the goalie's not there. If the goalie's there, they'll pass it to someone else. For the most part, when we were looking at that picture, how were we looking at that picture? It's a little bit different now that we move back, but for the most part, it looked like we were looking almost straight down at it. Would it look very different if we came in at an angle? Well, you know, I don't know if it's going to be far enough to really see it. But it doesn't look different from different angles. I'd love like a hockey shot over here, coming. Do you see much of a difference? Or are we not getting enough of an angle? What do people think? Yeah, it doesn't seem that big. So that when the dots are being put on, it almost seems like it doesn't really matter that much.
And one thing that's interesting about that too is that this is a print, not, for example, the oil painting. So if you look like, it's also a print, like the American Studies 307 up there, or I'm trying to think of another good example in here. There's a term that we use in art history called impasto, and that's building paint. So if you can think of like a chunky, if that makes sense, painting. If you looked at dots where there was a thickness to them, think of a Monet, if you've ever seen a Monet, or even some Van Gogh depending. If you looked at that from an angle, you would see the dots projecting out. So you would almost see the depth of it, which you wouldn't really notice looking at it straight on. With something like this, it's a print, so everything has the same kind of thickness to it. It's not like some dots are thicker than others. So it can still appear different, but what's interesting is that with an oil, you might actually get a physicality. You might get a 3-dimension from the dimension of the paint being built up over time.
Was there another item here you wanted to show us? Or?
Not in this room, but there's 2 other different galleries.
Okay, so let's go to the other 2 galleries.
Okay.
Was there any other questions here?
What's interesting to me about this one is that it's like 2 upper half space projections onto a 2-dimensional surface, and some function between the 2 by reflection.
Which, I mean, that's interesting, of course, with the water.
Yeah, exactly.
One of my favorite artists is Thomas Eakins, and it was discovered years after his death that he would take photographs and project them onto the canvas and put little dots so that he would get the perspectives right without having to spend all the time.
So why don't we start with this one really close up again?
So make sure nobody's behind Greg so that he can walk backwards.
So what do you guys see here?
Besides me. Wow.
So just looking really up close, not trying to make sense of significance, but just what do you see?
A lot of black dots.
So definitely lots of dots. What color dots?
I would say it looks like all of the dots are the same color. And these like green red dots.
Like a blue violet almost, and then a red. So how many colors total do we have here?
I would guess 3.
So just all there is
Not the white.
there's, well, yes, there's the white background.
We're mathematicians, okay? So.
In addition to the background, Yeah, that would be the red dots and then the blue-violet dots. So looking up close though, is there anything that's not a dot? There's the white background. Is there anything that's not a dot or part of a dot?
So like over here, connecting these two blues, would you call that as part of a dot?
So if you look really, really up close, they are all part of dots. So you can see like this is like a sliver of a dot. Here's another sliver of a dot. So they look like lines, but as you look really up close, they are they're parts of dots, right? So now let's go to the center of the room.
Walking backwards.
I already did the.
Oh, you already did that. Okay, you already did the dramatic. Okay. So I thought there might be some.
So what do you guys see here? Do you see any dots? So what picture do you guys see? What color dots do you see? And again, different people can see different things, so it's not like there's an absolute correct answer here. But what color dots do you see as you go further back? Just be careful that painting right behind you does not have glaze on it. Do we see red dots anymore?
No.
What is the red in the shape of? Does this image from back here look familiar to anybody? It's quoting a famous, yeah.
Yeah, I don't remember the name, but it's kind of church facade that was a lot of impressionist kind of portraits over and over again. We're done with it.
Absolutely. Does anyone know the name of that artist? Yeah. Yeah, absolutely. So Monet, this is Rouen Cathedral, done by Monet. Monet did it hundreds of times. So if you've heard of like his haystacks or the water lilies, he would do these hundreds of times, different color palettes, different times of day, studying light effects and all of that. This artist is an American pop artist who did this print in a variety of different media, a variety of different colors. But the end effect was quoting that Monet's cathedral. When you look far back here, I personally see a red image that might have some kind of blue-purple dots on it. He's really famous for the dots where it's supposed to look kind of like a graphic novel, comic book, newspaper cartoon, where it has that kind of pixelated quality to it, the bed dots from printing. So it looks kind of like he's doing like a pop art riff on it. But it looks to me, it looked like this to the professors who talked about it for the show Label Talk, that there was almost like a blue screen maybe on top of the image that was making it pixelated. So when you looked at it from further away, people would have sworn that it was a red paint, like a solid picture of the cathedral with purple dots on top of it. But was that the case when you looked up close? It was absolutely all dots. And so just thinking again about how you get that resolution to be just so. And why did he have to use all dots in the first place? Like he didn't have to, it wasn't enforced on him.
Now, there's a very nice lattice pattern for the blue dots. And then we have the red stuff around it. But it looked like there were a lot of different choices for how the red looks. So the question would be, what if you limited yourself to, say, 5 or 6 different red shapes? How quickly could you approximate something like this now? How much do you really need those finer details for like the red crescents and lines and whatnot? Versus if you just restrict yourself to, I have to use part of a circle, but I can only use, say, 5 different cuts of a circle. What can I do now? You said there was one other?
And then there's one other one.
To me, it's also interesting as to where's the transition point. How far away do you go before you have the marked change in behavior?
And then this one here where we actually have a painting, it's not a print like the other two. So as you get closer to it, looking for different marks like we've been doing, but also looking for that thickness of paint that we talked about a little bit.
So this is the same scene? Or is it approximately the
This
same
is,
scene?
so the other one, yes, this is London again, and again by a French artist, about the same time period.
But is it essentially the same view of London? Or is it just similar?
I think it's just similar, but it's
Okay.
hard to tell because the other one is so kind
Right.
of vague, it is harder to tell. But they do look extremely similar, especially like as you're further back. The main scene is of this bridge, going to buildings, the boats, very similar composition.
And now I'm trying to see if you go from the real thing to So thank you again for having us, for putting together the pieces. So just to briefly sum up, what I want you to get out of today's tour is the power of perspective. How do you want to represent the information? What are the choices you're going to make? And how is that going to influence how you look at the problem? One of the difficulties of teaching multiple classes is you sometimes forget what you did in which class. And so I know we did generating functions and the moment generating function proof with the central limit theorem. In my probability class this year, I had the sum of s to the n times the probability that x equals n. And the students had no idea what it was. But then when I switched the order, and I wrote as the probability x equals n times s to the n, they said, oh, it's the generating function. And just a very small twist in terms of just the order in which you present things. It guides people in terms of how you look at things. We used notation like if f is your function, big F is some kind of nice transform. Maybe it's the Laplace transform, maybe it's the antiderivative. And that gives you an idea when you quickly glance down to see what's going on. Notation matters. And so when you're choosing how to present things, you're making a choice. And the choice you make is going to impact on whether or not you're able to see how things fit together. And so the purpose of today is to just think a little bit about the choices you're making, the perspective you want, and which features truly matter. In an ideal world, we would be able to visualize 4-dimensional functions of 8-dimensional variables. We can't do that. So on Monday, and I'll send you some stuff to read over the weekend. This is Wednesday, right? So plenty of time to read this stuff. I will send you some stuff to read to just get you ready for several complex variables. We're not going to do too much on several complex variables. I want to do enough for you to just realize how different several complex variables is from one. This is almost like the old SATs. Several complex variables is to one complex variable, as one complex variable is to, real analysis. Just the remarkable change that happens as the geometry. If you continue in topology, you'll see that there's some things that are going on in dimensions 3, 4, and 5, and then by the time you get to higher dimensions, you have enough space to move around that these obstructions vanish. And it all comes down to, if you're a visual person, and a lot of us are, how do you actually get that information so you can make these connections? So thank you very much for the film work. We'll see how well you did.